So far, we've been taking a look at electric fields. And what sort of thing causes an electric field? To create an electric field, what do you need to have? Yeah, you got to have a charge, which we typically call a source charge. The source charge creates electric field in the space around it. And then what does that electric field do to other charges? Yeah, it exerts a force on other charges, which we usually call the test charge. So this is our usual schematic for just how we deal with electric effects. And of course, what's really happening is the source charge and the test charge are exerting forces on each other. But it's mathematically useful to insert this extra step here. Say the source charge or charges create an electric field in the space around them. Once you know the electric field, you can ignore the source charges and say the electric field itself creates a force on the test charge or charges. So electric field is just a property of this empty point in space, but it tells you how much force would be experienced by a charge if there was a charge placed at that location. And we can deal with magnetic fields in a very similar way. We can say a magnetic field, much like an electric field, in this case written as capital B, the B field, the magnetic field, is this invisible lines or arrows drawn in space. It doesn't necessarily have a direct physical meaning, much like the electric field doesn't necessarily mean there's anything physical at that location. The electric field is describing how much force could be experienced by a test charge if you put one there. The magnetic field is a similar idea. It doesn't mean there's something physically there. It's describing in some ways what would happen to a test object if placed there. And what has to be happening to create a magnetic field in the first place? It's not just created by any charge. What does the source charge have to be doing to create a magnetic field? Yeah, it's got to be moving. A moving source charge creates a magnetic field. So if you have just a charged object, it creates an electric field, but it doesn't create a magnetic field. If the charged object is moving, it creates an electric field because it's charged and also a magnetic field because it's moving. So a magnetic field requires the source charge to be moving. And likewise, the magnetic field can exert a force on other objects. But it exerts a force on moving test charges. So the magnetic field is created by a moving charged object, and it exerts a force on other moving charged objects. There's got to be some sort of motion involved, but that motion can take various different forms. And much in the same way that we've got different equations relating the source charge to the electric field versus equations relating the electric field to the force. For example, electric field caused by a point charge is K times Q over R squared, versus the force exerted on the test object is charge of the test object times electric field. Different formulas because we're talking about different sorts of interactions. The electric field that's created by a source charge versus the force that's felt by a test charge because of that electric field. Similarly, we're going to have different formulas for these two interactions. Formulas and other rules for the way a source charge that's moving creates a magnetic field, and other formulas and rules for the way a magnetic field exerts a force on a moving test charge. Any questions on that general outline so far? So let's take a look at some examples here. First of all, the idea of moving charge can actually mean a variety of different things. Probably the simplest example to visualize would just be if you have some charged object. Let's say you've got an object whose charge is +3 coulombs. And let's say it is moving. It just has a velocity vector. Maybe it's moving at 10 meters per second to the right. That's a charged object. It's moving. That's moving charge, so it's going to create a magnetic field. Or if we treat this as the test object, we could say this moving charge could experience a force from some other magnetic field. But it's one or the other. You want to treat this as either the source object or the test object, not both at the same time. Either you're treating this as creating some magnetic field, or you're treating it as experiencing a force from somebody else's magnetic field. And one way to do this is to just take, like, let's say you just take a plastic ball, suck some of the electrons off of it so it's now positively charged, and throw it. That's moving charge. But that's not the only way to have charge moving. What's another way you could have charge moving in maybe a more predictable and controlled way? What's another kind of, current in a wire? The same, all the circuitry stuff we saw in 7D. If you've got, let's say, a simple circuit, you've got a battery, you've got a resistor, you've got current flowing. Current is also the motion of charge. We've got charge flowing through this wire. So current flowing in a wire creates a magnetic field. This is actually one of the earliest examples of the beginning of the understanding of how electricity and magnetism are related. This guy, Ørsted, in the 1800s, was doing some experiments with electrical circuits, and happened to have a compass next to the circuit. Turn on the electrical circuit and the compass twitches. That suggests that the electrical flow is causing a magnetic effect. So that suggests that current flowing in a wire causes a magnetic field. So in that case, we would call this the source current. It is moving charge. It's just charge flowing in a wire rather than a charged object moving in free space. But it still counts as moving charge. It still creates a magnetic field. Or alternatively, if you've got current flowing in a wire in the presence of somebody else's magnetic field, you could treat this wire with current as the test object and say that the wire with current experiences a force from something else's magnetic field. So moving a source, current flowing in a wire does count as moving charge for these purposes. One of the big differences between these, though, if you take a look at just a section of wire, what would you expect the total charge of that section of wire to be? In terms of its protons and electrons. Like if you just take a look at a section of wire, what would you expect about the number of protons versus the number of electrons in that object, that section of wire? Yeah, they should be equal. If you just take a section of copper wire, you just like spool out some copper wire from a spool of wire and cut it. This section of wire is neutrally charged. There's no reason to expect it to have more protons than electrons or more electrons than protons. So this section of wire is neutrally charged. And no total charge means it exerts no electric field. So a section of wire does not create an electric field, but it does create a magnetic field because within that wire, which particles are actually moving as current flows? Yeah, current is the flow of positive charge. And of course, what's really happening is you've got electrons traveling the other direction. But since current is just the flow of one type of charge, that is moving charge, so we get a magnetic field, even though the total charge is 0, so there's no electric field. So current flowing in a wire creates a magnetic field because some of the charge is moving, but does not create an electric field because the total charge is still 0. On the other hand, if you've got just an object that has charge and it's moving, that's a charged object, so it creates an electric field, and it's moving, so it also creates a magnetic field. So you can have some situations where there's an electric field and a magnetic field, some situations where there's a magnetic field but no electric field. Or alternatively, if this object were just staying still, it would create an electric field but no magnetic field. So it's possible to have any of those situations. Any questions on that so far? And one other thing also, so far we've been talking about moving charge, a charged object in motion or current flowing in a wire. But those aren't the only ways to get magnetic fields. In fact, in everyday life, when we talk about magnets, we're usually not talking about current or charged objects at all. What do we typically expect magnetic effects from? Where do we usually see that in everyday life? Yeah, magnets, just a permanent magnet. I've got a magnet attached to this wooden block here. If I just stick this to the board, that's not because there's charge on this that's being thrown. It's not because there's current flowing in a loop of wire. It just sticks. There's magnetic attraction, magnetic forces, because of what's going on inside this lump of metal. What's that lump of metal made of? At the smallest possible level. What's any matter made of, really? Yeah, atoms. If you take a look at the individual atoms, in this case, I think iron, or maybe some other metal, but let's say iron for now. If you have one single iron atom, what's that atom itself made of? Yeah, protons and electrons. And neutrons, but we don't really care about the neutrons because they don't have any charge anyway. But where are the protons located versus where are the electrons located? Right, protons are in the middle and staying still. So they since they're staying still, they do not create a magnetic field. But the electrons are on the outer edges and moving around. So the electrons on those outer edges moving around do create a magnetic field. Also, what's the total charge of this entire atom? Yeah, total charge is 0. There's no electric field because the total charge of the atom is 0. It's neutrally charged. But there is a magnetic field because the negative charges are moving and the positive charges are not. If all the charges were moving, like let's say you've got negative charges and positive charges all moving together, then there's overall no magnetic field. All the magnetic effects cancel out. But if you've got electrons moving while the protons stay still, we do get a magnetic field. In fact, the magnetic field you end up with here, if you actually map this out, it ends up looking kind of like a very strong magnetic field in one direction through the center. And then kind of looping around the outer edges. And we'll get into more detail about why it's shaped like this later. But you'll end up with this sort of shape kind of like this. In fact, that's very similar to the shape of what sort of electric field we were looking at earlier. What sort of electric effect, or electric, yeah, an electric dipole. An electric dipole, if you take a look at a positive charge and a negative charge as a dipole, the electric field that creates is outwards from the positive, inwards towards the negative, and looping around. And it turns out that the magnetic field caused by electrons whizzing around in a loop like this, or also current flowing in a loop also has this effect, creates a magnetic field that's the same shape, roughly, as the electric dipole electric field. So because it creates a magnetic field shaped like this, we call this one atom a magnetic dipole. So every iron atom is a magnetic dipole. Does that mean every lump of iron is magnetic? Like, can you take any two lumps of iron and they'll stick together like magnets? No, not every lump of iron is magnetic. If you take a look at the individual atoms that make up a single block of iron, let's say you've got a block of iron made up of all these atoms. Let's say a very small block of iron that's only 6 atoms for now. If you just have each one of these acting as a magnetic dipole, like let's say this one has a magnetic dipole moment that points this way, and this one has a dipole moment that points this way, and this one's pointing this way, and they're just randomly aligned. If you've got these random alignments of vectors and you add all of them up, what would you expect a whole bunch of random vectors to add up to? Yeah, they should add up to 0. And if you've just got 6, that's not necessarily going to be true. But if you've got lots and lots of atoms, and each one has the same strength magnetic field, because they're all the same type of atom, but they're all pointing in random directions, then on average, you're going to have the same amount pointing left and right, same amount pointing up and down, same amount pointing forward and backwards, so they all cancel out. So an ordinary lump of iron would have a total magnetic field of 0. It does not act like a magnetic dipole because all the individual fields cancel out. But if we take that same lump of iron, those same atoms, and let's say we put this in the presence of an already existing magnetic field, a magnetic field from some other source, something else. Maybe we put a wire with a strong current nearby. Maybe there's current flowing through a wire, and we put this lump of iron near that current. In that case, what would you expect a dipole to do in the presence of a field? Do you remember what happened to the electric dipole in the presence of the electric field? Yeah, it's going to flip to be in the same direction, or at least it's going to experience a torque pushing it towards that direction. If you've got a magnetic dipole, such as an individual iron atom, and there's an existing magnetic field from somewhere else, all those individual atoms are going to experience a torque pushing them towards aligning with the existing magnetic field. So if this magnetic field is strong enough, all these iron atoms are going to rotate, they're going to swivel to align with the existing magnetic field. And this only happens in certain metals, iron and a few others. Other situations, I think the atoms aren't able to swivel in the same way. But the individual atoms all being aligned means now these vectors, if we add these vectors together, what's going to happen? If you add together a whole bunch of vectors in the same direction, what do you get? Yeah, you get a net result, a very large net result. Exactly, it's not going to be 0. If they're all pointing in random directions, we'd expect them to cancel out, or mostly cancel out. But if they have all been given this bias to be pointing in the same direction, that means the total magnetic field caused by this iron is going to be very large. This lump of iron now has its own magnetic dipole moment. So that means this lump of iron does act as a magnetic dipole. The original inert lump of iron with just randomly scattered atoms does not act as a dipole, but it becomes a dipole. It becomes magnetically polarized if you put it in the presence of another magnetic field, because all the atoms get swiveled to align with the existing magnetic field. Now all of their dipole moments add together and you get a very strong dipole moment in total. And we described this for the electric dipole, we had a positive end and a negative end. For the magnetic dipole, this isn't caused by like a concentration of charge or anything like that. It's all about the directionality of the atoms, which way they're oriented. So instead, we describe this region as the north end of the magnet, and this region as the south end of the magnet. So the dipole moment, and also the magnetic vectors are pointing outwards from the north end and inwards towards the south. If we drew out the magnetic field from this magnet itself, it would have a magnetic field that looks like this, curling around, because this is a dipole. So in general, if you've got a magnetic dipole, because all of the atoms are oriented in roughly the same way, you're going to have an end that we call the north end, and that's the end that all of these magnetic field lines seem to come out of. And the end that we call the south end, that's the end that all these field lines seem to go into. Except within the magnetic field goes this way, from the south end towards the north end. Because one of the important properties of the magnetic field lines is that they're continuous. This magnetic field line doesn't just stop when it gets to the south end. It goes through the magnet and forms a loop. This is one of the most important differences between magnetic field lines and electric field lines. Electric field lines tend to start at a positive charge and end at a negative charge. These magnetic field lines don't start anywhere and stop anywhere. They just form a loop. So this is one of the biggest differences between a magnetic field versus an electric field. Electric field lines usually start at a positive charge and end at a negative charge. Magnetic field lines don't start or end anywhere. They form loops. So, and you can actually measure this by cutting open the magnet. How would you usually determine the direction of the magnetic field? Like if you know there's a magnetic field here and you want to determine what's the direction right here, what tool could you use to measure the direction of the magnetic field? Yeah, the compass. The right-hand rule can be useful for doing the calculations if you're trying to predict what direction the magnetic field will point under certain circumstances. But if you've got a physical situation, you want to know what's the direction of the magnetic field at this location, you take a compass and put the compass here. The compass is a little magnetized needle on a swivel mount, which itself is a magnetic dipole, the needle. And so the needle is going to swivel to align with the existing magnetic field. So if you just place a compass somewhere, the compass is going to swivel to align with the existing magnetic field. That tells you the direction of the magnetic field at that location. If you want to measure the magnetic field inside a magnet, what you can do is cut a hole in the magnet, put the compass in that hole, and the compass will swivel to align with the magnetic field inside the magnetized region. So from that, you can tell that the magnetic field is pointing this way if you're inside the magnet. And it does form loops rather than starting or ending anywhere. One of the other important properties of a bar magnet like this, let me redraw it over here. So we've got all of these individual atoms, each of which is oriented the same way. And we've got a north end and a south end, which is defined in terms of the way the magnets, the way the individual atoms are oriented. If we cut that in half, though, let's say you break your magnet into two pieces. Do we now have a north object and a south object? No. What do you get if you break the magnet in half? Yeah, you get two magnets, each one of which has a north end and a south end. Because north and south in this context are not about what particles are there or not there. North and south is about the directionality of the individual atoms within the bar magnet. So this object has a north end and a south end because of the way the atoms are oriented inside it. This object also has a north end and a south end because of the way the individual atoms are oriented inside it. This is very different from an electric dipole, because an electric dipole is polarized because it has a bunch of positive charge on one end and a bunch of negative charge on the other. If you break that in half, you don't have two dipoles. You have a positively charged object and a negatively charged object. Because electric polarization is all about where the positive and negative charges physically are. But magnetic polarization is about which direction the atoms are oriented. So that's really one of the biggest differences here. There's a lot of similar behavior in terms of the dipoles and which direction they point and stuff like that. But there's a big difference in behavior in terms of what happens if you break it. Any other questions on that so far?
I had one, Casey, just to
Yeah.
clarify, the reason that like the magnetic field is working different than like the electric one here is because of the movement through them. Like even though it's halved or however you choose to cut it, that
Mhm.
like current is still running through it, so there's still invariably going to be a north and south end, versus because the electric field is stagnant, it's just like that's the distribution of the charges. There's no like rate involved, and so like
Right.
if you were to cut it, there's no movement, so that's why nothing else happens.
Yeah, and for the electric dipole, I mean, the positive end means physically there's not enough electrons on this end. And the negative end means there's too many electrons on this end. If you break this in half, this piece still has not enough electrons, and this piece still has too many electrons. So the charges stay where they are. But when we say this is the north end and the south end of a magnet, we're not saying there's north particles here. We're not saying there's south particles here. There's no such thing as north particles and south particles. North and south are talking about which direction the individual atoms are aligned and the motion of charge within those individual atoms. So if you break this in half, you're not changing which direction the atoms are pointing. The atoms in this piece are still pointing in this direction, so we still have a north end and a south end. The atoms in this piece are also still pointing in this direction, so we still have a north end and a south end. Any other questions on that so far? So there's really three different types of moving charge that can do this. You can have a charged object that's moving, like if you just take a plastic ball, charge it up, and throw it. That counts as moving charge. You can have current flowing through a wire. If you've got a wire and maybe it's attached to a battery or something and you've got current flowing through it, that also counts as moving charge. And also these individual magnetized atoms. Certain types of atoms, notably iron and some other metals, each individual atom of that type acts as a magnetic dipole in its own right because of the motion of electrons within the atom. If you've got a lot of those atoms clustered together and they're all pointing in the same way or approximately the same way, then that lump of iron counts as a magnet. It creates its own magnetic dipole moment and its own magnetic field. And that's going to form these characteristic loop shapes, and therefore it counts as a dipole. Any other questions on that so far? Then let's take a look at this idea of the right-hand rule or right-hand rules. There's several of them we got to be able to use. And the right-hand rules largely have to do with the idea of current or motion of charge creating magnetic field, or experiencing a force from a magnetic field. As one example, let's say we have current flowing in a wire. Let's say we've got a wire that is horizontal. And let's say there is current flowing from left to right. And presumably this wire is part of a larger circuit. I'm going to just draw these dots on the end. These dots mean there's more current, there's more wires attached to this, more parts of the circuit. We're just not showing them. We're only looking at this piece of wire. This piece of wire has current flowing to the right. That is moving charge, so it should create a magnetic field. And to figure out what that magnetic field looks like, let's say we want to focus on one single location. Let's say a location, let's say above the wire. So we want to know the magnetic field at this location. And there are a few ways you can determine this. One important thing to look for is you take a look at the radius vector. Radius in the sense of the line between the location of interest and the wire itself that's causing it. So this is the radius. And you could think of that as a vector. Just the radial distance between the point of interest and the wire that's causing it. One of the important things about the magnetic field is that it's always going to be perpendicular to both the flow of charge itself and perpendicular to the radius vector. And this largely just has to do with the way we define magnetic field in the first place. The magnetic field is always going to be perpendicular to the movement of charge. I should say the movement of the source charge. In this case, that's going to be the current in the wire. Or if you've got a charged object that's moving, the magnetic field would be perpendicular to the velocity of that charged object. And the magnetic field is always going to be perpendicular to the radius vector. Radius in the sense of the displacement, the distance between the source current and the point of interest. So if we have radius that is vertical, so here's our radius vector, and we've got a current that's flowing in this direction, so there's our current. Radius and current, what are the only possible directions that are perpendicular to both of those? Yeah, either straight out of the board or straight into the board. So those are the only possible directions for the magnetic field in this context. Just based on these perpendicular properties, the idea that the magnetic field has to be perpendicular to the radius and perpendicular to the flow of charge, the only possibilities are straight out, in other words, towards the viewer, and straight in, away from the viewer. So based on the perpendicular properties, we can narrow it down to two possible directions: outwards or inwards. And this is the same outwards and inwards notation we saw in 7b, a vector like an arrow pointing straight towards you versus an arrow pointing straight away from you. So to choose one of those, this is what the right-hand rule is all about. Any right-hand rule is about choosing one of those two once you've narrowed it down to two possibilities. And it doesn't have to be outwards or inwards. It really varies depending on which direction the radius and the current are going to be. So in this case, you could use, there's several variations on this. One way is if you put your hand, and this is especially useful if you're looking at just one location. Put your hand at that one location, stretch out your fingers straight towards where the source wire is, and curl your fingers in the direction current is flowing. Once again, that's put your hand at the location of interest, right hand specifically. Stretch out your fingers straight along the radius vector towards the source wire, the thing causing the field. And note that the current is flowing to the right, so curl your fingers to the right, and your thumb should then tell you the direction of the magnetic field. So this suggests an outwards magnetic field here. Again, that's put your hand at the point of interest, stretch out towards the source, swivel so you can curl your fingers in the direction of the motion of charge, and your thumb should tell you the direction of the magnetic field. So this should be an outward magnetic field here. And that's usually called the first right-hand rule, or a right-hand rule of the first type. And yes, there's another way you can do this also. There's multiple different ways you can do this. The method I just showed, I find usually most useful if you're looking at one single location. If you just care about this one location, you can put your hand at that location, stretch out towards the source, curl your fingers in the direction of current, and your thumb tells you the direction of the magnetic field. Or alternatively, you can point your thumb in the direction of current and imagine wrapping your fingers around the wire. Above, my fingers are pointing outwards. So that suggests an outwards magnetic field above. So either of those methods would be called the first right-hand rule. They're just different variations on the first right-hand rule. And they describe the relationship between the magnetic field and the motion that causes it. Yes, if the source is a negatively charged object in motion, then you would switch the direction. For example, if we have, let's say we have a negatively charged object that is moving towards you. And we want to know the magnetic field, let's say over here. Once again, I would start by narrowing it down to two possible directions using the perpendicular properties. If we draw in the radius, And we know that we've got velocity pointing outwards. So velocity pointing out of the board and radius to the right. So what are the two possible directions that are perpendicular to both of these vectors? If you got motion towards you and radius to the right, what directions are perpendicular to both of those? Yeah, up and down are the only possible directions perpendicular to both of these. So we know that the magnetic field at this location has to be either straight up or straight down. And once again, we would choose one of those two using a right-hand rule. And again, we could use either of those variations. You could put your hand at the point of interest, stretch out towards the location of the source charge, and curl in the direction it's moving, which in this case is towards the viewer. So that would suggest an upwards magnetic field, except this is a negative charge, so it's actually the opposite effect. This would be a downwards magnetic field. So the magnetic field here at this location would be downwards. Or alternatively, you could point your thumb in the direction of the charge's motion, outwards, and the curl of your fingers wrapped around to this side would be upwards. But again, since it's a negative charge, that gets reversed and it's actually downwards. Another way you could do that, by the way, is treat a negative charge moving one way as if it's a positive charge moving the other way. Negative charge moving towards you is equivalent to a positive charge moving away from you. So point your thumb in the direction it's not moving, curl your fingers, and now we have downwards on this side. Or if we were looking at another location, let's say a point directly above. We draw in a radius vector. So we now have radius upwards and motion outwards. Based on these two vectors, what are the only directions perpendicular to both of those? Yeah, left and right. So the only possible options for the magnetic field here would be left or right. And again, we could use either of those right-hand rules to figure that out. For instance, put your hand at the point of interest, stretch out your fingers straight towards the source charge, curl your fingers in the direction it's moving. That suggests to the left. But again, it's a negative charge, so that reverses the effect, and it's actually to the right. Or let's say we were looking at this point sort of diagonally down here. There's our radius vector. What possible directions would be perpendicular to this radius vector? Yeah, they're going to be diagonals, either up and to the left or down and to the right. Those would be the directions perpendicular to this radius vector. In and out are not actually going to work here. In and out would be perpendicular to the radius vector, but they wouldn't be perpendicular to the direction of motion. We need vectors that are perpendicular to the direction of motion and the direction of the radius vector. So the only vectors perpendicular to motion and radius would be this direction, because that's perpendicular to both, and this direction. So up and to the left or down and to the right. So those are the only options for the magnetic field here. So, and again, to choose which one, you could put your hand at the pivot point, stretch out, make it easier from this side, stretch out along the radius vector towards the source charge, and curl your fingers in the direction of motion. Now my thumb is pointing down and to the right. So down and to the right would be the magnetic field, except what type of charge is this? Negative, so that reverses it. So we actually get up and to the left. And you could keep doing this all over the place around this charge. You'd end up with magnetic fields that look kind of like this. And note that these all form a loop. Radius vector is just the distance between the points of interest that you care about in the source charge. And so that's going to be different at different locations. Like this location here would have a larger radius vector. And by the way, what would you expect to happen to the magnetic field as you get further away from the source? Yeah, we're going to get a weaker magnetic field as you get further away, or a stronger magnetic field if you're closer. So distance does matter here. However, since this tends to form a circular pattern, this loop-shaped pattern around the motion of the source charge, we don't necessarily need to draw in all the vectors. We can just draw in field lines showing the general trend. And then closer in, the field lines are going to get more tightly packed. Field lines closer together, showing a stronger vector field. And then further away, they'd be more spread out. But note that these field lines form loops. And any single field line is going to form, a magnetic field line forms a loop back on itself. They never start or end in a single location. Yeah, another the right-hand rule, let's say specifically for this location. One method is put your hand at the location of interest, stretch out towards the charge that's causing the field, curl your fingers in the direction of motion, and your thumb tells you the direction of the magnetic field. Except this is a negative source charge, so we reverse that. That suggests downward magnetic field at this location. Or alternatively, to get this general idea of the circulation, if you've got a charge moving this direction, we should expect the magnetic field to be forming loops around that velocity vector, either loops this way or loops the other direction. So if you know the velocity vector of the charged object, or alternatively, if you know the wire's location in space, you know the magnetic field should be forming circular loops around that velocity vector or around that wire. The only question really is, are they forming loops clockwise or counterclockwise around that vector, around that axis? And the other variation of the first right-hand rule is very useful for that. This is a negative charge moving in the outwards direction. So if you just point your thumb in the direction of motion of charge, the natural curl of your fingers should tell you the direction of the circulation of those loops. Except again, this is a negative charge, so that reverses it. Alternatively, as your right-hand rule, if you've got a negative charge moving, just pretend it's moving in the other direction. Negative charge moving towards you is equivalent to positive charge moving away from you. So you get this circulation. Circulation, I guess from your perspective, that would be clockwise. So that's usually called, or both of those are just variations of what's called the first right-hand rule. The first right-hand rule is all about this interaction of the moving source charge creating the magnetic field. The first right-hand rule. And there's various variations on that. There's also the second right-hand rule, which is all about the force exerted on a moving test charge. The second right-hand rule, which is usually using a three-finger sort of setup, three fingers perpendicular to each other. Typically, the way that is set up is your thumb is used for the velocity of the test object. So whichever direction the test object is moving, that's your thumb. Your first finger is the direction of the magnetic field from something else. And your middle finger, perpendicular to those, tells you the direction of the force on the test object. So velocity of the test object, magnetic field caused by something else, and force on the test object. So that's the second right-hand rule. And we can get into more examples of that next time. Any other questions on magnetic fields in general or the first right-hand rule before we go? All right, then I will see you next time. You're welcome.
Thank you.